And I am back. Told you I'd be back. All right, number 7. We're cranking. Some good stuff this week. How do you and I been together? We the theory this week wouldn't have taken too long. I mean, yeah, there's 8 problems to do, but some are pretty quick. The lab would have taken a long time. The lab was really labor intensive for this one. Properties of acids and bases. I did. If you've watched that yet at this point, I did 2 parts of it for you as demonstrations. I demonstrated for you, and 2 parts you're going to have to look them up. So, but that was a very labor intensive for a long time to measure things out. If we were in the lab, it takes like 3 hours. All right, so good thing, right? Good thing that maybe you weren't here for that. But it is a fun lab, though. It is fun. All right, number 7. Calculate the percent ionization. 0.6 molar hydrofluoric acid. So hydrofluoric is not, sounds like it should be, but it's not one of the strong acids. It's a weak acid. So that means that it will break down, but then reform. We'll have an equilibrium with it. It will not be arrow one direction. Okay, one direction. I was so upset when they broke up. You know, I really liked them. I like Liam, he was my favorite. So H and F. There's my acid breaks down. Initially, I'll have some of this. Then it'll change over time. Yes, ice charts. Ice charts everywhere, and not a drop to drink. Rhyme of the Ancient Mariner. Read it. It's good. Actually, I didn't really like it. I had to read it. 7th grade. All right, it did give me the concentration of the hydrofluoric to start, 0.6, so at least I got that going for me in this problem. I didn't have to calculate it like I did last time. 0.6. Okay, none of this, lose this, gain this, gain this. See, becoming redundant. You should be able to do these in your sleep by now. 0.6, or if you're not doing it in your sleep, you will be soon. X and X. The K expression, remember K equals products over reactants. So K, I need the K value for the hydrofluoric acid, 7.1 times 10 to the negative 4th. So K is 7.1 times 10 to the negative 4th. X squared, 0.6 minus X. Let's see if we can get rid of that X. Let's do our rule of 100. Remember, we take the initial concentration, 0.6, and divide it by the equilibrium constant. 7.1 negative 4. And we get 1,267. So yes, well above 100. So you are small and insignificant. You're small and insignificant. You don't matter. That was kind of harsh, wasn't it? Poor little guy. Again, cross multiply, take the square root. Okay. Cross multiply, take the square root. You can do it. You can do it. Water boy. You can do it. Water boy. One Adam Sandler movie which is watchable. I don't know. I'm just not a big Adam Sandler fan. I mean, some are pretty good, though. I mean, some are pretty good. Waterboy's pretty good. Okay, Happy Gilmore. That was pretty good. Wedding Singer. All right, not bad, not bad. Okay. Forgot what I was doing. Oh, yeah, I'm multiplying. 7.1 exponent negative 4. Enter. Second function square root, second function answer, enter, and we get 0.0206. 0.0206. So 0.0206. I'll make it 0.021. Actually, you know what? I forgot what we were even doing in this problem. I was just so excited to get the ice chart done that I just dove right in. And we did it. Yay! What are we doing? Let's find out. Oh, yeah. Calculate the percent ionization. What? The percent ionization? This is a weak acid, so it doesn't ionize 100%. What percent does it ionize? 1%, 5%, 10%? What percent is it ionizing? Well, how do you get percent? You know, any percent, you always take the blank and divide it by the blank. partial divided by whole. Partial, partial, partial. Everybody's always talking about partial. Oh, that was Marcia. Never mind, Brady Bunch. So to get a percent of anything, and in this case we're going to get the percent of ionization, we are going to take the partial. What part of it did ionize? What portion did ionize? Boom. Boom. Check it. X is equal to, there it is, H. I put it over here. H, yes. H is equal to 0.021. That's the amount that did ionize. It's what the hydrogen concentration became. That's the amount that we have ionized. So we take the partial, what did ionize, take the partial, what did ionize, divided by the whole. What could have ionized if it were a strong acid? If this were a strong acid, all of that 0.6 would become hydrogen. It would all break down. Remember, that was the original concentration. This is molar, remember. These concentrations are molar. So 0.6 molar, the initial concentration, I would add 0.6 of the hydrogen if this were strong. It's not, it's weak. So my partial, this is the amount that did ionize divided by the potential of the whole, 0.6. Go ahead and, looks like it's going to be like 3 or something like that. 0.021 divided by 0.6 equals 0.035. Now, remember how to get a percent. You've got to multiply by 100. So 0.035 times 100, 3.5%. So 3.5% of that acid ionized. And that's actually not bad for a weak acid. Weak acids are usually less percent breakdown than that. So that's actually pretty good. It was a 10 to the negative 4. Still small for the K value. The K value is 10 to the negative 4. And the last problem, the acetic acid was 10 to the negative 5. So that one breaks down even less. So remember, these K values go along with how much they break down. And this one, negative 4, is a bigger number than negative 5. So, but still, it's small, and not a lot of it breaks down. 3.5% ionized. All right. Yeah, that was it. That was it. That was pretty good. That was pretty quick, right? Okay. Percent. Partial divided by whole. So take the amount of hydrogen that we were able to get and divide it by the amount of hydrogen we could have got if it all broke down. All right. Uno más, muchachos grande.